Great job in chunk number 1. We are already on chunk number 2 of our 3 chunks for this week. And chunk number 2 is going to start our next unit, unit 2 on functions. And chunk number 2, we just get a kind of soft start to functions as we describe some words and learn some words that help us describe functions. So this week in our new unit, Unit 2 Functions, we're going to focus on our first learning target, which is identifying functions and describing their conditions. So we're going to learn a lot of words that allow us to describe functions as we learn what functions are this week. So open up your note packet. We're going to be on page 1 as we travel and work through some of these notes together. So first off, we've just got a lot of words to describe a function. So we want to match these words with the picture they go with. So I'm going to go ahead and kind of keep this easy. And letter A, any words that describe this first graph, letter A, I'm going to circle in this pink color. So you can write the word next to the graph, you can draw arrows, whatever is easiest for you. But we want to find the words from this list that describe this graph, letter A. So as we go from left to right looking at our graph, this graph is increasing. It's going up. It also, another word for increasing could be gains. Gains is kind of just a synonym for increasing. Another kind of synonym would be improves. This graph is improving, it's increasing, it's gaining, and those would be my 3 words to describe letter A. Now graph letter B is doing just the opposite. As we see from left to right, it's going down. Our arrow is going down. So the words to describe this graph are going to be decreasing. Reducing could be another word for that. Or declines, it's going down. And we'll see in our last graph, we've got only 3 words left, so we can probably guess where they go. But the word constant, this graph is staying the same. The line is remaining the same, it's not going up, it's not going down. Or the words no change here, nothing is changing, it's staying the same. So here's a ton of words we could use as we describe some graphs or some situations in this unit. Now 2 big words, and we saw this last week when we worked with the Desmos activity with the eggs in the carton. So we can have different types of functions. We can have a continuous function or a discontinuous function, which better known as, we might call this discrete, could be another word. So let's also have this one written down. So let's notice the difference. I see in the pictures here that these continuous and discrete functions look different. But if we wanted to really describe the difference between these, when we look at a continuous function, if I was going to trace or draw this function, notice from one end to the other end, I would never need to pick up my pencil when graphing this. So from start to finish, my pencil stays on the paper, and I would never need to pick this up. Now, as I look at a discrete function, this looks like more so some points. We might also, if we remember our egg graph from Desmos, it looked kind of like this. So they weren't points, but they were disconnected lines. So if we ever have distinct or separate points or lines on a graph, we know this is going to be discrete. We would have to pick up our pencil as we create the graph. So, for example, if I looked at these points, point, pick up my pencil, point, pick up my pencil, so forth, as I'm creating this graph. So there's going to be some different situations as we talk about functions, and it'll be great to make sense of when we need something to be continuous. So we're including decimals, parts of things, and when we have something that's discrete, which is a specific, distinct value. So let's look at our first example here. We're going to match A, B, and C with the graphs above using some of that language that we saw in our first part of this lesson. So this first one, we're saying we're gradually increasing our speed. So we want to look in our graph for a line that is going up. We're increasing. So I see the first and the third currently work for that. Then we're going down a hill. So notice we're comparing our speed with time. So if we go down a hill, we have to be careful here because our speed is actually going to get much faster. So our line is going to go up, it's going to continue to go up, and it will be very steep. Then you're going to come to a stop at an intersection. So the speed is going to get slower and slower all the way to the end. So we'll see letter A goes with this first example. Pause the video and try and match letter B and letter C to our next two graphs. All right, welcome back. Next one says you gradually increase your speed, so we know we need to start by going up. Then we stop at a store, so our graph is going back down to a stop. We're there for a few minutes, so we're not moving, our speed is staying the same. And then we continue to ride, we're increasing that speed again. So letter B will go with this last graph, which tells us letter C goes here, but let's read it. You ride at a constant speed, so we're saying the same speed. Then you go up a hill. So if you've ever ridden a bike, you know when you go up a hill, unless you're super, super strong, I suppose, that your speed definitely goes a little bit slower. It slows down because it's hard work to go up a hill. Then we continue to ride, increasing our speed to the end here. So A, C, B. Now these get a little trickier. Now we're going to look at these graphs, and we're going to kind of try and create a situation for something that could be happening. So why don't you pause the video and try and create a situation, and then unpause to compare with something I came up with. So this first one here, we're comparing the age of a person with their height. So my description for this first example would be, we're looking here, would be you're growing at a constant rate, so we're increasing at a constant rate, and then you have a quick growth spurt. Notice how this line goes up pretty steep. So you have a quick growth spurt, then you remain that height for a little while, and then you start growing at a constant rate again. So notice words I said there, increasing at a constant rate, described my lines that looked like this. A steeper line, we had a growth spurt. Remaining the same was this section. Those were some key words that I used as I described this graph. All right, our next one is comparing servings with calories. So if I were to describe this, I would say, let's say each serving of a Kit Kat that you eat, you're continuing to eat more calories. So if I have one serving here, I have a certain amount of calories. 2 servings, another amount of calories. And as my servings are going up, my calories are also increasing. The more I eat, the more calories I'm eating. Now this is an important question to ask, and this is something that makes Functions such a great unit. Functions is going to be a lot of conversations and kind of proving your story with what you're thinking. So in this one, I noticed that this graph is discrete, which means we've got our separate points. But if we think about, could I eat 1.5 servings of something? And if the answer is yes, I think this graph could also be continuous if we wanted. So we could make an argument for, is this person eating parts of servings, or is this person eating just 1 serving, 2 serving, 3 serving right on the dot? So that's going to be some of the great conversations we get to have with continuous versus discrete examples. Sometimes it can go both ways. All right, now we're going to create a graph to describe the situation. So you'll notice for this first one, we don't have any numbers on our graph, but we're comparing time with speed. So we have a stopped subway, which means we're starting here at 0, our speed is 0. It is gaining speed at a constant rate. So gaining tells us we're going up. Constant means it's going to be that straight line there. It reaches its maximum speed, and then it travels at this speed for a while. So now we're going to stay at the same speed for a while. Then it's going to slow down at a constant rate, so another straight line until it comes to a stop at the next station. So our graph should look something along these lines here. Now our last example here, creating these graphs. We are looking at a pet store that's selling puppies. These puppies are $50 each. So since we actually have numbers in this example, we better put some numbers on our graph. The pet store has 8 puppies to sell, so we want to sketch a graph for this situation. So we've got puppies on the bottom, so let's go ahead and mark these. We know we need to go up to 8. We'll give ourselves a nice scale here. And money, we're going up. We have 50, and then we'll go 100, 150, 200, 250, 300, 350, 400. Okay, take a second and fill in your graph as you think this graph would be created to describe this situation. All right, welcome back. Now, this is a wonderful, wonderful example to talk about because if we sold 1 puppy, the pet store is making $50. 2 puppies, 100. We can continue to follow this trend. 3 is 150, 200, 250, 300, 350, all the way to our end here. We've got these points. Now we have to be very, very careful because when you create your graph, we could also put 0, 0 here. We do not want a line through these points. Now I know it's habit to draw that line through the points as we've worked with linear functions in the past, but we have to make sense of this. This is a real scenario for us. So if we drew a line through these points, could we have part of a puppy? Could we purchase 1.5 puppies? Would be my question to you. And hopefully we say the answer is no. Okay, we can purchase 1 full puppy or 2 full puppies or 8 full puppies, but we cannot have parts of a puppy. So this is actually a great example of a graph that has to be discrete. We can't really debate this one. Okay, so this graph, and I want you to erase your line if you drew a line through these points. This graph is discrete. Now a couple more little logistics as we describe functions. You guys are doing wonderful with this. We've got 4 representations that we're going to see as we talk about functions. We just saw a lot of graphs as we looked at these first words, but we could have things like a mapping diagram. So we'll notice here as we look at this mapping diagram, we can think of this like a table, that these are my x's and these are my y's. And my x, my 0 in my x here, goes with 2 in my y's. So we'll see here, 0, 2 looks like this in the table, and 0, 2 looks like this as a point, and 0, 2 looks like this on the graph. So as we look at these 4 kind of representations, these are the 4 ways that we can represent a function. So we have to be able to look at all 4 of these things and decide if something is a function or not. So last 2 examples here. We've got a list of points, and we want to take these points and express them as a table, a mapping diagram, and a graph. So we'll notice since these are specific sets of points, we're going to have a discrete picture here. So let's start with our table. We have our x's and our y's. My first point is 1, 5. Second point, 2, 3. Third point, 3, 2. Fourth point, 4, 1. There's my table. Now a mapping diagram looks very similar. We have our x's, we have our y's. My x's are 1, 2, 3, 4. My y's, we'll put these in order here, 1, 2, 3, and 5. And now our arrows are actually indicating which number goes where. So with my x, my 1 goes to my 5. 2 goes with 3, 3 goes with 2, and 4 goes with 1. And now for our graph, We're going to plot these 4 points. We have 1, 5, 2, 3, 3, 2, 4, 1. So here are all 4 of our representations: our points, our table, our mapping diagram, our graph. Pause the video and try this example. And this is actually our last example for today. Then unpause to check. So as we create our table here, we have our x's and our y's. Our x's, we have 1, 2, 1, -2. With 1 goes 3, 2 is 5, 1 is -2, -2 is 4. Now let's create our mapping diagram. Now, one thing that's unique about a mapping diagram, and I want you to fix this if we made a mistake on this piece, is we are only going to write our values 1 time in a mapping diagram. So although in my table I see 2 number 1s for my x's, in our mapping diagram my x's are just going to have 1 of these 1s. Now we'll go -2, 3, 4, and 5. So -2x goes with 4, 1 goes with 3, and it goes with -2. So you'll notice because we have 2 arrows, that shows we have 2 x values of number 1. And then 2, 5 for our last one here. And let's graph this. We have 1, 3, 2, 5, 1, -2, -2, 4. So again, we have a discrete example. These are just points on our graph, no lines. But we have our points, we have our table, our mapping diagram, and our graph. Wonderful, wonderful first part of this unit, you guys. Great job.